Hello ladies and gentlemen, good to see you again. This is lecture 3, week 3 for GGS300 quantitative methods for geographical analysis. In today's lecture we're going to be focusing on descriptive statistics. Before we begin, I'm going to be focusing on a couple of course updates. So I've set the first homework now, and you should be submitting it today. The second homework I'll be setting today, again, will be due next week on the Thursday. I didn't receive too many questions. I had a few, I was able to help a few people out where they were stuck. I don't know if this is a good sign or a bad sign. So if you do have issues in the future, please don't hesitate to reach out to me. I think that it's good for you to engage with me, even if they're just small questions, and then hopefully you can get the most out of this module. I did have one suggestion, and that's that I might consider kicking off an online discussion so that people can discuss the use of quantitative methods for geographical analysis. And I think that this is a pretty good idea, and it means that you're able to engage with your peers as you go through this process. So next week I'm going to begin a discussion which you can all contribute to. I'm not entirely sure what the structure of that's going to be yet in terms of whether it's marked or not, but I might revise the marking scheme if people aren't necessarily going to participate. Then I may have to proportion part of the overall mark to that particular activity to ensure that everyone engages. So I'll let you know if I do end up updating the course outline document. I know that there is a newly updated course outline which is available on Blackboard, as I put some extra pieces in there relating to the course, a very detailed overview of each of the individual weeks and what the homework was going to be, and then also a couple of points about how the work is set and submitted and things like this. So do take a look at that if you get a moment. So today the purpose is to introduce you to descriptive statistical concepts and techniques. Arguably this is an easier part of the syllabus than the inferential statistics, which we're going to get onto later in the course. So enjoy these few weeks. So before we begin, I'm going to give you an overview of some of the key concepts of descriptive statistics before we get into some of the technical ways in which we actually calculate some of the metrics which are used within this area. So what exactly are descriptive statistics? Well, they're any type of metric or any type of numerical information which can summarize the key characteristics of a data set. And what's interesting about this is that they are highly relevant to how we understand statistics as a whole, because there are certain underlying statistical properties which all data sets exhibit. And if you're able to then identify what these properties are, you're able to understand the process that maybe you're trying to understand, whether that's a physical geographical process or a spatial human interaction process. And then when you know how this process behaves in terms of its quantitative statistical characteristics, you're then able to have a holistic understanding as to how this process carries out. And that's really powerful. So it is quite abstract from the actual phenomenon of interest, but that's the beauty of statistical analysis, that you're able to then use it to understand key factors which affect how that process takes place. I'll try to pull in quite a few examples to give you a bit more understanding as to how we use some of these in actual projects, and I'll try to keep the theory and high-level detail to a minimum. But I'm going to start with some really easy examples. So my question therefore is, well, what do these two factors have in common, these two areas? So height measurements is just one example, and then as a second example, the rolling of multiple dice or die. So they are essentially normally distributed. So what do we mean by that? That means that the values that these the values that we obtain when we take either measurements for height, for example, or when we roll multiple dice, exhibit similar statistical properties. So they fall into that category as having these similar shapes, for example, when we actually produce a plot of the distribution of the values. And you can see here from the height of females in North America that this shape does in fact look like a bell, and that's one reason why it's often called the bell curve. But this is really important. A lot of classical statistical techniques rely on data having this underlying distribution, whereby you basically have an average, a mean, which is approximately in the middle of the distribution, and then as you go out towards the more extreme values, you essentially have fewer individual entities in those areas. So I've already spoken about females. Heights are a good example of this. But then on the right hand side as well, if you had dice and you rolled two of them and then you summed the values that they would produce, you would be more likely to achieve values which were in the middle of the range that you could possibly get, so between 2 and 12. Okay. So we covered some of this in the previous lectures, where essentially we focused on what the scientific method is, why we carry out quantitative analysis, and we focused on the fact that we have descriptive statistics as one part of a more basic set of methods to understand how the world works, and then we have inferential statistics as a potentially more complex, more advanced way to understand how the world works. So in this lecture, we're going to be focusing on the red square here. And for example, we could, using these approaches, develop questions to investigate. So maybe we state some hypotheses about physical or social geographical processes that we want to understand. We then go out and we collect that data, and then we would prepare that data maybe in R or some other type of data processing software. At least 90% of your research time will be spent preparing data, so data munging, so changing the structure of that data to get it in the right format so that then you can carry out the statistical analysis. So I was always shocked when I first heard that, and I don't think I really thought it was true. But a lot of the time you spend most of your effort getting the data, making sure it's in the right format, and then actually the bit where you do the statistics you could do relatively quickly at that point, but it might take you months to get to that particular point in time. So then you can process the data and you can develop a set of descriptive statistical metrics, and that can inform conclusions which we reach. Then you can either formulate new hypotheses or go on to essentially test certain hypotheses using other statistical techniques. So we have these two different branches, and we'll be focusing on the left-hand one today. So what's a parameter, and what exactly are statistics? Well, in this case, within what we're talking about here, parameters refer to describing the entire population, and generally we have a set of parameters that we use within statistics to denote, for example, the population size as a capital N, or the population mean as mu, which you can see here. We covered these in the previous lectures, but they're going to be pretty important for how we carry out some of those metrics, how we calculate those metrics later in this class. And so these are key parameters, mainly of the population at large. Statistics, therefore, in contrast, within our framework here, are more likely to relate to the sample of a population. So if you remember that it's highly expensive to go out and to actually census or speak to every individual, or get information from every place that you want, you might carry out a sample, a representative sample of the overall population. And therefore we would denote these statistics in different ways. So we might refer to the mean of the sample as x bar, as we do here and we will do in this lecture. And we might also refer to the number of samples in our sample as n, or here it's lowercase n, essentially. But it's important to recognize these because I'll present you with the way to calculate these statistics using math, or we will also look at how we calculate them in R in a more practical way. But it's important to understand both of these, particularly if you want to go on and do more advanced research. Now we can summarize data sets essentially with a variety of different metrics. So firstly, we think about the measure of central tendency. So that's that certain properties of data sets have a tendency to cluster around certain values, potentially around the center of the distribution, such as the mean. So we may be interested in understanding the degree to which a data set conforms to levels of central tendency. We may also be interested in the spread of the data. So actually this first value here, it relates to key ways in which we may summarize the whole data set down to a single value. So you all have heard of these before. So that's the arithmetic mean, the median or the mode. And then actually these measures of dispersion here are about how the data may be spread around those values. So the level of variation, the standard distribution, for example, standard deviation. And then finally, we may be interested in the shape or the relative position of that data distribution. So is it skewed to one particular direction? Why does it display that particular skew? How can we quantify that particular shape change? Then there are actually a large number of potential ways in which you could correct for some of those defects in your data if they don't conform to the sort of classical requirements that are needed to do inferential statistics, as we'll be doing later in this term. So there's these three different ways in which we can understand data sets using descriptive techniques, essentially. So let's start with those individual values first then. So what is the mode? Well, the mode is the most frequently occurring value. So here is just an example of some data values, and you can see that 20 is the most frequently occurring. So there's a single number which represents that most frequent value. However, there may be times where you have multiple peaks in a distribution. For example, the distribution may be bimodal. So it may have two peaks like down here, or you may have many different peaks within the data because it's multimodal. But this is a very simple way to characterize data. And actually, within my own work, I don't really use the mode at all. Maybe that's because this type of metric is more akin to maybe what you would use if you were collecting nominal data, and I don't do that much qualitative data analysis, and therefore most of my work relates to continuous measures which are much more suited to either the median or the mean, for example. So what is the median? Well, it's the middle value when you have a set of ordered values within a data set for a particular parameter, for example. So there's an equal number of data points above or below it, and it's very useful if you have a data distribution which is quite skewed. And I'll get more into this at a later date. Essentially, how do we calculate the median then? Well, firstly, we need to order the data to begin with from the smallest to the largest. And then it matters whether the sample size is odd or even, but then essentially we can either find the middle number or the average of the two numbers around the middle number, which then provides us with an understanding of what the median value is. So in this lecture here now, we're going to be talking about this at quite a high level, but in the laboratory, we're going to actually be working out how to calculate these metrics within the RStudio environment that we've been using so far this term. I just want to relate this to something which I know you'll have a greater understanding of. So when we talk about the median, it's quite high level unless you've already done some statistical analysis. But if we think about the distribution of household incomes, for example, so this data is from the Census Bureau, and if we think about the shape of this distribution, it's highly skewed, positively skewed, and that means that the tail moves out here towards the right. And essentially that's because when we think about income, there are some individuals who earn an awful lot of money, and as a consequence, then when you look at the distribution of those incomes, they can go from, most people here earning beneath $200,000 a year per household, all the way up to where Jeff Bezos is, Mark Zuckerberg, pretty much all of the tech entrepreneurs, Warren Buffett, Bill Gates, at the other end of the distribution, essentially. And now this is a problem. This is a problem because if we just wanted to take the average of that particular distribution, those individuals like Warren Buffett would skew the whole, would bias the estimate that we produce, essentially, because the average would be very, very high above the median value, which is more what we're interested in when we think about income distribution, because we want to understand where, say, 50% of households sit. And you can quite clearly see that here because we have the 50th percentile, or otherwise here we can treat it as the median value, which therefore helps us get a better understanding of how the large majority of the population sit in terms of income. So the arithmetic mean, you probably all calculated this before. Essentially, it provides an average for a set of data values, and the way that we calculate it is essentially by summing all of those values and then dividing by the total number of values that we actually have. So here I provide the math for calculating the sample mean. So essentially, to get the sample mean, which is x bar, as I mentioned before, we basically need to sum up all values of x across all of the index points within the data sample. So from I up to 10, if we have 10 values in our data set, and then we need to divide it by the total number of values that we have, and that's how we obtain the average. The population mean mu, we do the same, but we basically we calculate that based on the population, the number of people in the population, and that's obviously going to be different. So although the math is the same for both of these metrics, the actual nomenclature, so the way that we actually specify these in terms of whether it's x bar or mu as the mean, essentially, is different. And that's important because you will see when you're reading papers or in the literature that people refer specifically to maybe just the letter, and then you need to kind of decipher what's happening in the paper based on that, because obviously here this is being spelled out in quite a simplistic way, but then when you read an academic paper, there's going to be a lot of existing knowledge which is just assumed, and therefore it can be very hard to start reading academic papers early in your career because maybe you don't have all of that background knowledge. So, so this is important. Now there are problems with the mean in that it may not take into account the fact that if you have groups and you average those groups, there may be more people in some groups with that value than others, and therefore what you may want to do is to actually take a weighted average. So that can be really useful, for example, to ensure that you actually get an aggregated mean which is closer to what the true mean is, especially if the data is already grouped. So how do we exactly do that? So just a reminder, we're going to calculate this in RStudio. So here I just want to explain essentially that to get the weighted X bar value as we get here, essentially we need to take the midpoint or the average for all of those individual groups, and we need to basically multiply it by the number of individuals within that group. And then we need to do that for each one of those groups that we have and add them together, and then actually we divide it by the number of total number of values. Okay, so we'll do this again in detail in the lab, but this is actually a really nice way to calculate the mean when you do have lots of different groups. And in fact, if you went back here and you just chose deciles, and you took the average income in just for 10 buckets, 10 bins along this distribution, this would be a prime example as to why you would want a weighted mean rather than an average mean, because if you didn't take a weighted mean, then your very high earners would really bias that estimate upwards. Whereas if you then weighted it based on the number of people, so the height of these bars in the histogram, then that would give you a mean that's closer to the value that you're really seeking, so the truth value. And this just gives you an example of how we actually calculate that in reality. So say that we have the average temperature for DC over the summer months, but we want to calculate the daily average for the entire span. Then we would need to use the weighting mean as we've done here, and this is how you would work it out by hand or in an Excel spreadsheet. And then you can come up with an estimate that is fairly sensible. And the same here again, if you were interested in home values in a city block, you may want to control for different areas, and that will give you a mean that's closer to the overall truth value, rather than just grouping and ignoring the number of houses that have actually sold at those different values. So when should you actually use different metrics? So I've just emphasized here, as I didn't define it before, that the central tendency is essentially the actual clustering of values of a random variable, and its distribution around the mean, or the mode, or the median. And so that's important. So when should we actually use each of these different variables? Well, essentially we have those 4 different types of data which we covered previously in the previous lectures, and essentially, sorry, someone just came to my door. And essentially, there are different metrics which are most suited for those. So, for example, when you have nominal data, I mentioned before about categories, data categories, you may be more akin to using the mode, so the most frequently occurring value. So if you did a survey, for example, and you asked people about which sports team they use, then maybe that would be the most relevant. And then if you had ordinal data, so they were categories, but they had some sort of ordering within them, then you would be best suited to use the median value. And then if you had interval ratio data, depending on the level of the skew, then you might use either the mean or the median. So the example that I gave you of income distribution is a classic example here of why you should use a median rather than a mean value, because the data values are heavily skewed. Okay, great. So they're measures of central tendency. Now we're going to delve into the data range, the interquartile range, and the standard deviation. So what is the range? Well, that's the difference between the largest and the smallest values within an interval ratio data set. So you don't necessarily see the range reported that often. So if you were going to look at a paper and they report the descriptive statistics, they may put it in there, but they're probably also They may put the minimum and the maximum value from which you're then able to derive the range. But they're more likely to have things such as the median and the mode, the number of samples in each category maybe that's there. And then maybe also the interquartile range, depending on how the data is being presented. But we'll get more to that when we use box plots later in this lecture. So quantiles. So quantiles are really useful. It just means that you're able to equally portion up your data set, and that's very powerful. So if we think before, the median was essentially just partitioning the data set into two, and then we basically picked the middle value depending on whether there were even or odd numbers an even or odd number of values in the total data set. But often we'd want to go to more lengths so that we had greater division of data. So it's very common for there to be quartiles, so 4 equal data sets, and that provides you with a nice understanding of where data values fall within the top half or the bottom half, or the quartiles at the most extreme ranges, the quarters at the most extreme ranges. And we'll cover this more when we get to the box plots. I don't use quintiles that often. They don't provide you with that much additional detail after just using standard quartiles. But deciles I'm a big fan of, and I use them regularly. So remember we spoke before about accuracy and precision, and often I use deciles when I know that what I'm working with doesn't allow me to be too precise, and therefore I need to control for how many individual bins I might be trying to guess predictions for. And that's why I kind of like it, because it provides you with more nuance than quartiles, but without going to the other extremes of, say, using percentiles. You will all be familiar with percentiles, so just imagine that these are essentially like percentage values, so between 0 and 100, and therefore you have 100 buckets within your set. Obviously here we're using integers, so round numbers, whole numbers, and therefore you can't have, you're grouping any value that's not a whole number, so decimal, like say 95.5 would go into the 95th or the 96th percentile, so it would fall into those buckets. But these quantiles are really useful, and you probably will use them if you've been using ArcMap or QGIS or one of those spatial mapping programs that is taught to actually produce visualizations for spatial data. So when you create a choropleth map and you color different areas based on the size of the values that you've got, you're able to select how you create the buckets for the color scale. And this is a good example of how you can change those. So you may use deciles because that's a really handy way to show 10 different colors. Or you could just show quartiles if you just wanted to put them into 4 different buckets. But this is a really handy tool. So I think we mentioned box plots previously. I think we did. But essentially, these are really fantastic ways. Oh, that's right. I spoke about John Tukey in the first lecture, and he's the person who actually invented box plots. And essentially, these are a really nice way to show these types of descriptive statistics across in a very simple way for a single category. So here we're interested in the interquartile range, which essentially in a box plot is this distance between the top of the box and the bottom. But actually the box plot itself is able to show so the mean value down here, the median value, and the whiskers generally represent the most extreme values. They're actually within 1.5 of the interquartile range of the box. But you do get outliers as well. But these are really nice because then you can just visually show people, right, this was the distribution, and these are the key metrics that I'm interested in. And then you can do that for lots of different categories, and you can produce lots of pretty plots where you show these. So I've been using box plots recently, and I just wanted to give you an example of how you might produce them and use them. And one of the questions which I've been working on is what percentage of annual gross domestic product would a country need to invest in 5G over the next few years to provide universal service so that everyone has access to high-speed broadband, basically. Now, gross domestic product is the amount of value that's created in an economy. So it's a measure of wealth overall. So imagine countries are compared in terms of the level of GDP that they produce. Obviously, it's not that easy to compare across countries when you use the raw values, because some countries like the US have almost $20 trillion worth of gross domestic product, whereas many other countries, for example, if you're looking at low or middle income countries, may only have very small gross domestic product. So even under 100 billion, if you're looking at a country, a very small country, for example, on the African continent. So that's why we're focusing here on the percentage of gross domestic product that each country would want to would need to invest. And I did a clustering exercise. So I clustered all of these different countries in the world into different buckets. So imagine these buckets as just being countries which have similar economic development metrics. So they're at a similar stage of development. And I'm focusing here just on low and middle income countries, okay? So we have on this top part here, we have clusters 1 to 6. So these are categories. Actually, you could think of these as an ordinal scale in terms of development, but just think of them now as categories. And essentially, across these 3 different metrics, I put countries into these 3 buckets if they were similar in terms of their GDP per capita, so the amount of value that they create per person, how populated each place is, so the population density, and what the existing 4G coverage is. And I just wanted to show you here a map of those countries which fall into each of the clusters, so that the following graph that I show makes sense. So here we're using box and whisker plots, and you can see the mean value. That's what's represented by the middle line, and then we have the interquartile range, and then the most extreme values at each end, so the whiskers. These are essentially correlated with development metrics. So anyway, now we know what those 6 clusters are. I'm able to present here what the gross domestic product percentage would need to be if you basically needed to invest it in different scenarios or strategies. So this is how much capacity we might possibly want to give each country. So from a small amount of capacity, so 25 megabits per second. So think with 25 meg, you can probably do quite a lot. You can almost stream high definition video on your cell phone or at home, for example. And then a more extreme, at the extreme level of the scale, we have scenarios which involve trying to deliver 400 megabits per second, so very large amounts. And then we have a set of strategies here. But the point is then we're able to show how the distribution of countries within each of these clusters is actually distributed across each of these scenarios and strategies. And therefore we can see for less developed countries, like in the first cluster here, which included lots of Central African countries, East African countries, they would need to invest a very large percentage of GDP to deliver 5G at a universal service level. Whereas smaller countries or more developed countries, which includes Albania, Peru, and Mexico, then they would only need to invest a smaller amount overall for a variety of reasons. They're geographically smaller, but also their GDP is much larger. So anyway, this is a practical example of how I actually use these statistics in my current work. Actually, all of these plots have been produced within R Studio. So it gives you a good example of what you can do when you're able to bring various data sets together and then, as I've done here, combine into a single plot sets of box plots, but also then the country diagram with the colours correlating to each category. And that can be really powerful. So, how do we understand the level of dispersion around that mean value that we're interested in? Well, the standard deviation is the way that we do this. So each deviation around the mean value is essentially squared, averaged, and then it's placed back into the same units by using a square root. And we can calculate the sample standard deviation as we will do in the lab. And this obviously looks scary, but it's actually quite a simple calculation. So to get the standard deviation, we're subtracting the mean, the sample mean, so x bar, from each value that we have in that data set. So xi, x1, x2, x3, for example, all the way through the entire data set. They're squared and then they're divided by the number of degrees of freedom. So I've spoken about this before, I will get to this shortly, but essentially just imagine it's the number of values in the data set minus 1. And then they're square rooted back to the same unit for interpretation. And actually it's the same math again for the population standard deviation, it's just that we've changed some of the nomenclature. So for example, we have sigma as the population standard deviation. So this value here, this Greek letter. And then we have mu as the population mean. And we have the total number of values in the population as capital N. So I know you're going to ask, why do we have a different denominator here when we compare these two metrics? So we have n-1 versus the total number of values. But the issue is that essentially when you have very small samples, you might end up underestimating the actual population standard deviation. So that's why we use n-1. When n is large, the difference between n and n-1 is very small, so it doesn't really matter so much. But it does matter with small samples. Generally, I don't really like working with small samples anyway for exactly this issue, which is that you start to get strange answers. You're not always sure how representative your data are. I do appreciate that in some areas you are constrained by the data. So one example is if you took high income countries and you were interested in metrics across those types of countries, then you would only get a small number of samples such as this. So if you take the OECD countries, so that's the Organization for Economic Development, OECD, Organization for Economic Cooperation and Development. If you take the OECD countries, I think you only have something like 20 countries to work from. So if you had data at the national level, then it would only provide you with a very small data set. And that's why when you see people doing that type of macroeconomic econometric analysis of statistics and economics, they have to do all sorts of funky corrections to the data to make sure they're not creating biased results. So here using the degrees of freedom means that the denominator is slightly smaller, and that means that we avoid biasing the estimator. So that's the key point here. So we've spoken about those measures of dispersion. Now we want to consider variance and the coefficient of variation. So essentially, the average squared deviations from the mean represent the amount of variance that's within the data. So you can think of this as essentially the square of the standard deviation. So we go through the calculation that we carried out previously for standard deviation, but we don't take the square root and put the units back into the same units as the actual data. But it provides us with an understanding of how far a set of numbers essentially spread out from their average value. And again, we have different nomenclature for calculating the sample variance as opposed to the wider population variance. And then we also have the coefficient of variation, which is a standardized score. So the standard deviation is an absolute measure of variability across all data, but it means that that can be difficult to compare when you're among different locations or at different times. So just to give you one example, imagine that we have 40 years of rainfall data. The mean for Buffalo, for example, might be approximately 35 inches, and the standard deviation may be about 4.7 inches. And then we have the data for San Diego, obviously a lot hotter, a lot further south, probably rains a lot less. It's in California after all. And therefore the actual mean for the level of precipitation is a lot lower. It's about 9.62. And the standard deviation, actually, it's quite similar overall for most values. But what we may be interested in is what the variability is between these different cities. So which city has the higher variability overall? So as I said before, the coefficient of variation is a standardized measure, which sometimes we actually present as percentage. But it shows us the dispersion. It measures the dispersion for a probability or frequency distribution. So if the coefficient of variation is low, then basically there's less dispersion. And then essentially if the coefficient of variation is high, then there's greater variation around the mean. So essentially we can calculate that by dividing the standard deviation, the standard deviation which we have here, by x bar, so the actual mean value that we have for the sample, and then multiplying it by 100. And then that gives us a coefficient, so we can think of this as a percentage, so it's between 0 and 100 for the level of variation that we have around the mean. And what this is telling us essentially is that Buffalo has a lower variation than San Diego, and part of this may relate to the mean value. So for example, Buffalo gets quite a bit of rain, whereas the precipitation levels annually are much lower in San Diego. But as a consequence, when San Diego does get a lot of rain, there could be a great deal more a higher amount of precipitation in comparison. So there's much more variable weather essentially. And this is just providing us with an understanding of how that data is spread, data are spread. Okay, so now we're going to focus on the level of skew and kurtosis within different data sets. So I've already mentioned this a few times, and we will look at the individual quantitative measures for how we actually calculate these metrics for different data variables in the laboratory. But essentially the skewness gives us an indication of the level of symmetry in a frequency distribution. So if the skew is 0, for example, then imagine that the data are normally distributed. So I mentioned before about the bell-shaped curve, and this is a good example. If the skewness is negative, then the tail goes out to the left-hand side. And then if the skewness is positive, then the tail moves out to the right-hand side, as I've already discussed when I was focusing on the income distribution. And we're actually able to calculate the skewness in the data. Essentially, it's quite similar to the other metrics, except this time we're actually raising to the power of 3. And we'll calculate this within the lab. But the skewness does affect how we understand the data. So the more extreme the skew, then the greater the level of dispersion around those central values. And this does actually then affect our ability to carry out a lot of the inferential statistical tests which we will do later within the course. And that's because there's all sorts of assumptions about the data being normally distributed and the ways, for example, that the error terms may be distributed, which we need to take into consideration when we're carrying out certain tests. And this is just one example of real-world data from a data set which I've been analysing on cell phone signals. So imagine you had 200 gigabytes of data from your phone signal actually being connected to the nearest cell tower. And actually a lot of these distributions are quite heavily skewed. So these are different operators, Vodafone, O2, E3, just imagine them as AT&T or Verizon. And then this is the level of signal on the x-axis, and the proportion of samples on the y-axis. And we can see over here we're getting some very skewed distributions, so negatively skewed in this case. And there are actual reasons why that happens, and it comes down to the way that they've designed their network and the available resources which they have. But I just wanted to demonstrate that this is something which we do come across in statistical data sets on a very frequent basis. So kurtosis represents the level of flatness in a frequency distribution. So if it is a very flat distribution, then we will refer to this as platykurtic. The way to remember that is that platypus is an animal which is considered very flat, and it's got the same name for that exact reason. So it's a flat distribution. Leptokurtic is essentially a peaked distribution. You can see it here in red. And mesokurtic is approximate flatness. But we were able to calculate this metric later. And I mentioned before, when I was talking about skewness, that these metrics are part of a series of different calculations that we're able to calculate for different metrics. So the first moment that we're able to obtain essentially is the mean. The second moment here, when we think about the moments of a distribution, is the variance. The third moment, obviously raising to the power of 3, is the skewness, and the fourth moment, as we're obtaining the kurtosis, is here as we raise to the power of 4. So that's the first. That's the third lecture on descriptive statistics. There's going to be a lab which follows, and we're actually going to generate these statistics. I'm going to show you how we do that, which is going to be very exciting. I hope this lecture was clear to you, and that I provided some examples of how we use these statistics. If there isn't anything that's not clear, you have the book. You have the book. Also, I would encourage you to look at YouTube videos if you need some additional content to help understand these topics. I appreciate that sometimes it takes multiple explanations to understand a concept. And then if none of those work, please don't hesitate to reach out to me, and I'll be able to assist with any queries that you might have. Okay, fantastic. I look forward to seeing you again, and have a good day. Thank you. Goodbye.